Hello student, I am Dr.A.K Sinha, Professor of Chemistry. Today I am going to discuss Ellingham diagram. Ellingham diagram. Last class I have discussed thermodynamic principle of metallurgy. In that I have discussed two relation, that is delta G is equal to delta H minus T into delta S, and second standard delta G is equal to minus RT ln K. On the basis of these two relation, we can decide that which reducing agent is suitable for reduction process and at what temperature. We get idea. Then this idea we get from the Ellingham diagram. Okay. Then what is actually Ellingham diagram? Now I am going to discuss. The graph or plot that this plot that is the delta Z, standard delta G versus temperature. Standard delta G versus temperature. This graph actually is called Ellingham diagram. The graphical representation of Gibbs energy was first used by Ellingham. Ellingham already told you a spelling Ellingham. Then in first time it was used by that H.J.T. Ellingham. Okay. This provides a sound basis for considering the choice of reducing agent in the reduction of oxides. This is known as Ellingham diagram. Again I am telling you, the graphical representation of Gibbs energy first time used by H.J.T. Ellingham. This provides a sound basis for considering the choice of reducing agent in the reduction of oxides. This is known as Ellingham diagram. Such diagrams helps us in predicting the feasibility of thermal reduction of an ore. The criterion of feasibility is that of a given temperature, Gibbs energy of reaction must be negative. This is the criteria condition, that at a given temperature Gibbs energy of the reaction must be negative. Means delta G must be negative. And one more relation is there. Actually delta G must be negative. This is the first condition for feasibility, means possibility for the reaction to take place. And other E electrode potential must be positive. Okay, both you keep in mind. If standard electrode potential is positive, then reaction will be spontaneous. First. Now second, delta G must be negative. Free energy change must be negative. Then these two relation you should remember always for a spontaneous reaction. Okay. And other two relation already I told you, delta G is equal to delta H minus T into delta S, and other relation standard delta is equal to minus RT ln K. Then this important criteria I told you that delta G must be negative at a given temperature. Okay, delta G means gives energy. Then these things, there are few points I want to tell you about the Ellingham diagram. First point I am telling you, Ellingham diagram normally consists of a plot of a delta G, standard delta G versus temperature for formation of oxides of elements. That is, for the reaction, in general I am talking about, that is 2xm plus O2, it will give 2mxO. Here x is the coefficient x, okay. Then 2xm plus O2, that is equal to 2mxO, means metal oxide. X value you don't know, maybe 1, maybe 2, sometimes maybe 3. Then in this reaction, means 2xm plus O2, it gives it 2mxO, just like M2O, M3O, MO, like that way. In this reaction, the gaseous amounts, hence molecular randomness you can tell. In this reaction, the gaseous amount is decreasing from left to right due to consumption of gases, leading to a negative value of delta S, which change the sign of the, you can say, second term. Now this 2xm plus O2, that is the 2mxO, the metal oxide. Then here that you know that this thing S, that is called entropy. Then entropy, change in entropy, that also I told you, already discussed in details. This is the measure of disorderliness. How any reactant went disordered, that is measured. Okay, and that is actually how much disorder went, how much disorder happened, that is called actually entropy, change in entropy, delta S. Okay, then this in any reaction, reactant gives a product. Hence, what will happen in this situation? Then in this type of reaction, the gaseous amount is decreasing, particularly in this reaction, is decreasing from left to right. Why? This is happened due to the consumption of gases leading to a negative value of delta S, because the entropy is changing. That's why it will be negative. Then product it is giving, means metal oxide is giving and leading to a negative value of delta S, which change the sign of the second term in the equation, above equation what I discussed. Subsequently, delta G shifts towards a higher side despite rising temperature T. Normally delta G decreases, that is the goes in lower side with increasing temperature. Means if temperature will increase, then delta G value goes to lower side, okay, with increase of temperature. The result will be, what will happen by this? If delta G decreases with increase of temperature, or it goes, delta G decreases, that is go to lower side. Delta G decreases means it goes to the lower side with increasing temperature. Then what will happen? The result is positive slope in the curve. You will get positive slope, okay, in the curve for most of the reaction. That will give positive slope for the formation of metal oxide. Whatever last class I discussed formation of metal oxide, in every cases slope will be positive. Okay, first point I told you that delta G value decreases. First things, and with the reaction that delta S will be negative. Okay, from left to right. Okay, from left to right, due to consumption of gases, delta S value decreases. It becomes negative value, and delta G value will be also negative. Delta G value also will be negative with increase of temperature. Okay. Now second point I am telling you of Ellingham diagram. The question is asked about the Ellingham diagram, what it is telling. Ellingham diagram, what does it tell? Okay, that I am telling. Second point. Here actually in Ellingham diagram I will send. Then in that you can see each plot is a straight line except when some change in phase takes place. Generally, if you will see the plot, then each plot is a straight line except when some change in phase takes place. Change in phase means suppose solid to liquid. Solid is converting to liquid or liquid is converting to gas. That is called change in phase. Then only that time it will be not a straight line. Otherwise it will be a straight line. Okay. Each plot is a straight line except when some change in phase takes place. The temperature at which such change occurs is indicated by an increase in the slope on positive side. Okay. If the temperature at which such change occurs means phase change. The temperature at which such change occurs is indicated by an increase in slope on positive side. That is, in the case of example I am telling you, in the case of Zn to Zno plot. Zno plot means Zn is converting to Zno. That's why it is written Zn, Zno. Zn metal is converting into oxide, Zn oxide plot. Then in this situation phase change takes place. The melting is indicated by an abrupt change in the curve. In this formation of oxide means Zn to Zno, melting point is indicated by an abrupt change in the curve. Okay. Third point, there is a point in a curve below which delta G is negative. Okay, very important point. There is a point in a curve below which delta G is negative. It means if it is negative means AMXO you can tell, or MXO metal oxide may be M2O, maybe MO, X may be 1, 2, 3 like that. Then it will show a stability. If it is negative, then it will be stable. Hence, there is a point in a curve below which delta G is negative. Okay, one point will be there. Below that, delta G is negative means oxide is stable. Above this point, MXO will decomposes on its own, and below this point it is negative means stable, but after that above this point it will decompose by own. Okay, it decomposes on its own. Now next point I am telling you, that is the fourth point. In an Ellingham diagram, the plot of a standard delta G for oxidation and therefore reduction also you can tell. When wherever oxidation is there, there will be reduction, that you know. For an Ellingham diagram, the plots of standard delta G for oxidation of a common metal and some reducing agents are given. Generally in a plot, not generally, it is given, it will be given. Okay, in Ellingham diagram, the plots of standard delta G for oxidation and also you can tell therefore a reduction of the corresponding species. Both when oxidation is there, obviously reduction will be there. Both process take place simultaneously. Then in that diagram, some common metals and some reducing agents are given. Always it will be given. Okay, common metals and some reducing agent, that will be given. You can understand it by seeing the diagram or plot. The value of standard delta G, that is the formation of oxide at different temperatures, are depicted, which make the interpretation easy. Now only in that diagram, in Ellingham diagram, values of delta G, because this is the delta G value versus temperature diagram. Hence the values of delta G, that is the formation of oxide. Okay, delta G for the formation of oxide at different temperatures are depicted. Means at what temperature, what is the value of delta G, easily you can know, because it is delta G versus T. Okay, then at any temperature what is the value of delta G, you can know, or at any particular delta G what is the temperature, that also you can know. That interpretation can be done easily. And last point, that is the fifth point of the diagram I am talking about, Ellingham diagram. Similar diagram are also constructed for sulfides and halides. Ellingham diagram, what I told, that is for oxide, formation of oxide from the metal to metal oxide, as for example Zn to Zno. But this similar diagram like Ellingham are also constructed for sulfides and halides, and it becomes clear why reduction of you can say metal sulfide is difficult. Actually formation of metal sulfide from the metal is difficult. Okay, you can see in a metal sulfide diagram only. Okay, and delta G of metal sulfide is not compensated. Delta G of metal sulfide is not compensated. Only by a diagram you can understand. Okay. Then 4 points I told you for the Ellingham diagram, and 5th point was similar diagram for sulfides and halides. Okay, it is difficult to construct. Okay, it becomes clear and very clear why reduction of metal sulfide is difficult. Okay, this I told about the Ellingham diagram. Correct, it predicts that at what temperature or at what delta G that metal will convert to metal oxide. Generally it is for metal oxide, and which this reducing agent is suitable, either carbon or carbon monoxide. Then in diagram it is written just near the plot that carbon or carbon monoxide, it is mentioned, it will be mentioned. You have to not do anything, only you have to see. Okay, and you can understand. Now actually I have discussed, I told positive point, but some limitation is also there. Question is asked, limitation of Ellingham diagram. That question is also asked. I told only positive points. Okay, but what are their negative points? Means limitation or failure, where it fails. Then 2 points are there, main 2 points are there. Limitation. Then first limitation I am talking about, the graph simply indicates whether a reaction is possible or not. In general way, actually it will tell only these things. This graph, exact position it will not tell. Exact means rate of reaction it will not tell. It will tell that it is feasible or not. Means reduction will take place or not, it will tell. The graph simply indicates whether a reaction is possible or not. That is the tendency of reduction with a reducing agent is indicated. Tendency, it tells about the tendency. It can predict the tendency of reduction with reducing agent is indicated. It will tell about that. Tendency, it tells about the tendency of reduction with reducing agent. This is indicated. This is so why it is indicating, I am telling you, it indicates only about this tendency that it will reduction will take place or not. This is so because it is based only on the thermodynamic concept. Okay, this indication, this prediction is based on the thermodynamic concept. It doesn't, now limitation you can see, it does not say about kinetics of the reaction. Kinetics of the reaction process means it can't tell, it can't answer, you can say answer questions like how fast it could be, it will be fast or slow, on how fast it could be. This Ellingham diagram will not tell. Means it does not say about the kinetics of the reduction process. Okay, whether it will be fast or slow. Only it will tell tendency, that tendency of reduction it will tell. This is the first limitation. Second limitation I am telling you, the interpretation of standard delta G is based on K. That you know that standard delta is equal to minus RT ln K. Hence it is based on K, equilibrium constant. The interpretation of delta G, standard delta G is based on K. You know delta G its standard delta is equal to minus RT ln K. Thus, it is presumed that the reactant and products are in equilibrium. When it is in equilibrium, then what K value, if you are knowing, only then you can tell correctly. Correct? Means this reactant and products always will be in equilibrium when you are talking about the kinetics. Okay. Then interpretation of standard delta G is based on K, because delta G, standard delta is equal to minus RT ln K, and K is related to kinetic equilibrium. It is the equilibrium, chemical equilibrium. Thus, it is presumed that the reactants and products are in equilibrium. Means metal oxide plus, you can say, A, it will give Xm plus AO2. Okay, metal oxide plus A may be reactant. A will be reduction, you can tell. Then reducing agent, what you can tell. Then it will give Xm plus AO. Correct? Then here you have seen that this is in equilibrium. This is not always true. This equilibrium I am talking about. This is not always true because the reactant product may be solid. This is only for liquid or gas. Equilibrium will be in case of liquid or gas, but not for solid. Hence, this is not always true because the reactant product may be solid. However, it explains how the reactions are sluggish when every species is in solid state and smooth. Okay. Because equilibrium takes place generally it is for gas and liquid, but sometimes it will be in solid state also. Okay. Then here this I told you that this is not always true because of the reactant or product may be solid. However, it explains how the reactions are sluggish when every species is in solid state and smooth when the ore metals or ore melts down. It is interesting here, you can understand, it is very interesting. It is interesting to note that delta H, that is the enthalpy change, and the delta S, that is the entropy change, these two values for any chemical reactions remains nearly constant even on varying temperature. These both terms will be generally constant, means delta H and delta S. So the only dominant variable is what? Only dominant variables in the equation is what? Temperature. Okay, temperature, and this temperature only, this is the variable. Okay, then dominant variable in, that is the equation, delta G is equal to delta H minus T into delta S, T becomes T. Okay, however, delta C, delta S, T is only a variable in the equation, but delta S, however, delta S depends much on the physical state of compound. Delta S, entropy, that is what is the measure of disorderliness. This is the this depends upon the physical state. Okay, delta S depends much on the physical state of the compound. Since entropy depends on disorder or randomness in the system, it will increase if a compound melts, okay, that you know, or vaporizes. Since molecular randomness increases on changing the phase, means from liquid to gas or from solid to liquid. Solid to liquid, that time it will change, or from liquid to vapor. When phase is changing, only that time randomness will change, means entropy will change. Okay, because that time phase changes. Since molecular randomness increases means delta S value will increase on changing the phase, okay, from solid to liquid or from liquid to gas. Okay, then I have told two limitation. First limitation, that it does not say about the kinetics of the reaction, and second, that interpretation of delta J is based on K. Thus you can tell it is presumed that the reactant and products are in equilibrium, and this is not always true, because the reactant product may be solid. Okay, this I have discussed limitation. Now I am telling you little more about the Ellingham diagram with some examples. The reducing agent forms its oxide. Reducing agent forms its oxide when the metal oxide is reduced. The role of reducing agent is to provide a standard delta G negative and large enough to make the sum of standard delta G of the two reaction, means oxidation of the reducing agent and reduction of the metal oxide negative, means both two reaction, overall reaction should be negative. Last class I have told you. Again I am telling you the role of reducing agent. First, you know that metal oxide, it has to convert to metal. Metal oxide will convert to the metal. That is our main distinction. What we want, objective. Metal oxide will convert to metal. For that purpose, reducing agent is used. Okay. Then the role of reducing agent is to provide a standard delta G negative and large enough to make the sum of standard delta G of two reaction. What are that two reaction? Then first is oxidation of reducing agent and reduction of metal oxide, means oxidizing agent negative. Okay, these two overall value of the delta G should be negative. Okay, means oxidation of reducing agent and reduction of oxidizing agent, means metal oxide. This should be negative. Finally, both reaction should be negative. Correct? Only then you can say delta G will be final delta G. If overall delta G value is negative, then both reaction will take place. Okay, and this metal oxide will convert to metal. Then now a simple general equation, that metal oxide MXO, M down XO, as for example M2O, like that way M2O, but you don't know whether X is 1 or 2. Then MXO will convert to XM plus XM means now solid, metal you got, plus half O2, because only one oxygen is there, half O2. Then this metal oxide is converted into metal solid, sometimes maybe liquid also, plus half O2. Then here in this reaction you see the reducing agent takes away the oxygen. Reducing agent, what it will do? It will take the oxygen, only metal will be left. The reducing agent from the metal oxide, metal oxide will lose the oxygen. The reducing agent takes away the oxygen, okay, and that time it will be oxidized. Okay, this is the important things. Means now metal XM plus half O2. XM now reverse case you can see, XM plus half O2, then MXO, both reaction, these two reaction take place, oxidation and as well as reduction, correct. First with MX plus this thing MXO, that converted to XM plus half O2, and reverse reaction, that is the XM plus half O2, that is the MXO. Then these two reactions should be finally negative, and how to represent this reaction in shortcut way? Then you should write MO arrow sign M, or simply you can write MO comma M, means metal oxide is converting into metal. And reverse way also you can write, for the second reaction, reverse reaction you can write M is converting into MO, M comma MO. In shortcut you can write like this way also, okay. Then here actually what you have to understand, that two reactions are there. Then you want actually metal from the metal oxide, then role of reducing agent will come. Then reducing agent, what it will do? First that actually oxide will form, means suppose carbon is there, suppose it is the reducing agent. Generally carbon is used as reducing agent, sometimes carbon monoxide, CO gas, carbon monoxide. Then here carbon will convert to carbon oxide, CO. Carbon it will take oxygen from the metal oxide, it will form CO, and metal will be free, it will convert to metal, correct. If CO you are using, carbon monoxide you are using, then carbon monoxide will again one more oxygen it can take, then CO will convert to CO2 and metal will be free, okay. Then here you have to understand in this way only, okay, that carbon C plus half O2, C plus 1 O means half O2 you can write, then C plus half O2, that is the CO, and again this CO again CO plus half O2, it will convert to CO2. Then in both these reaction, delta G value in both these two reactions, suppose C plus half O2, CO, then in this reaction delta G value will be there, it will have some delta G value. Then you can write delta G, and near the G you can write C comma CO. Delta G, and near the G you can write in a small letter that C comma CO. Like that way, CO is converting to CO2, then CO plus half O2. It will give CO2. That time you have to write that delta G CO comma CO2. Then these two reactions have delta G value. If carbon is taken, suppose carbon is taken, there may also be complete oxidation of element to CO2. Suppose a carbon you have taken, then carbon first it will convert to CO, and in second step CO plus again 1 O means half O2, then it will convert to CO2. Half CO plus half O2, half C plus half O2, then it will give CO2, half CO2, correct or not? Then this way also you can write. But in both cases, carbon is converting into carbon dioxide. Then in this situation, you will write half delta G, because half carbon, half O2, half CO2 you are getting. Half carbon is reacting with half O2. Then it is giving half CO2. Correct? Hence you can write half delta G value. You can write half delta G is equal to C is changing to CO2, C comma CO2. In the place of only delta G, now you can write half delta G, because all are half. You can't write complete delta G, half you can write. Okay. Then now here again I am telling you important things, that metal, suppose carbon is taken as a reducing agent, then metal oxide plus carbon, then what it will form? It will form XM, MX is there, X value don't know, maybe 1, maybe 2, okay. Then MX means it will give XM plus it will give CO, carbon monoxide gas, okay. And if we will take carbon monoxide as reducing agent, then MX plus CO, it will give XM plus CO2, correct. And if suppose you are taking half carbon, MXO plus half carbon, then it will give XM plus half CO2, correct. Then these reactions describe the actual reduction of the metal oxide. MXO, metal oxide is MXO, that we want to accomplish. The delta G, standard delta G value for this reaction in general can be obtained by similar subtraction of the corresponding delta G value. Suppose for all the reaction you are getting the, because for each reaction some delta G, standard delta G value will be there. Hence for a particular reaction how much delta G was required, then you can get it by subtraction, okay, by subtraction. For any particular reaction step, by subtraction you can get the value. As we have seen, heating, that heating means increasing temperature favors a negative value of delta G. This always remember. If we will heat, heating, that is the increasing temperature favors a negative value of delta G, standard delta G. Therefore, the temperature is chosen such that the sum of the standard delta G in the two combined redox process, reduction and oxidation, okay. Then because with increase of temperature delta G value increases, therefore the temperature is chosen such that the sum of the delta G, standard delta G in the two combined redox process is negative. In delta G standard versus T plot, this is indicated by the point of interaction of two curves. important point I am telling you. In in standard delta G, this graph I am talking about plot, delta G, standard delta G versus T plot. This point means this what temperature is required so that the sum of the delta G in the two complete redox process is negative. To know that temperature, this you can know what temperature is required for so that two combined redox process is negative. At what temperature it will happen, then that we can know by the Ellingham diagram, means delta G, standard delta G versus T plots. This is indicated by the point of intersection where both will cut. Two plot will intersect, they will cut to each other. Then that from that point see the down, what is the temperature. Okay, then that is the temperature at which both overall reaction will be negative, and below that temperature reduction will take place. Okay, this is the only important point. Where two plots are cutting, means from the point of intersection draw a line parallel to y-axis, means delta G. Then it will give the value of temperature, because that is a delta G versus T. T is on x-axis, delta G on y-axis. Then you will get the value of temperature. If a parallel to y-axis, you will draw the line from the point of intersection, then you will get the idea of temperature. At that temperature only you can say this overall delta G value will be negative. And what is actually value of delta G? Then you can see you can see that at that point parallel to x-axis, you can see on y what is the value of delta G. Just parallel to x-axis you saw towards on y-axis you saw from that point, from the point of intersection, what is the value of delta G. Correct? Then this important point I have discussed you, that what will be the temperature. Okay. Then this I have told you. After that point, the delta G, means after that point the delta G value becomes more negative. Okay, here you should understand that interaction, I told you interaction of two curves, curves for MXO and that for the oxidation of reducing substance. After that point, the delta G value becomes more negative for the combined process, including reduction of MXO. The difference in the two delta G values after that point determine whether the reduction of the oxide of the upper line is feasible by element represented by lower line. Two line will be there, both are intersection. Then I am talking about that two line. The difference in the two delta, for each line delta G value will be there. The difference in the two delta G values after that point determines whether reduction of the oxide of upper line is feasible by the element represented by lower line. Okay, if the difference is large, the reduction is easier. Difference if more are, means both are far distance is more, then obviously value will be delta G change in delta G value will be more, then reduction will be easy. Okay, then you have to see in the Ellingham diagram, always you see the, you can say, two curve you can see where they are cutting, what is the down temperature, and how much this differences are there for these two lines. Then this things, temperature you can see only on the x-axis, delta G you can see on y-axis, and how much differences is there between the two. If differences is more, then reduction will take place easily. Okay, now one to this things problem I will tell you, then easily you can understand. Okay, actually what I discussed Ellingham diagram, this is based on that only. Question is actually asked. Then here problem is there. Suggest a condition under which magnesium could reduce alumina. Alumina means L2O3. Then here very simple question is there. Suggest a condition. Condition you have to suggest. Suggest a condition under which magnesium could reduce alumina. Means magnesium aluminum reaction first you have to write. Then two reaction you can write. Aluminum plus oxygen, it will give Al2O3. Correct? Aluminum oxide, it will give aluminum plus oxygen, it will give aluminum oxide. Okay. Then now balance equation you will write, then 4/3 aluminum plus O2, it will give 2/3 Al2O3. This is a balanced reaction. 4/3 aluminum plus O2, it gives 2/3 Al2O3. It is balanced. This is the first reaction, means aluminum and oxygen. After the reaction it is giving aluminum oxide. Second, now role of magnesium will come. Then magnesium and oxygen, it will give magnesium oxide. Magnesium oxide means balanced equation, 2Mg plus O2, 2MgO. Then these two reaction you have to write to get the condition. To tell the condition, these two reaction you have to write. One reaction means one oxidation reaction with aluminum, other oxidation reaction with magnesium. Now after that you will see that this you can see only by Ellingham diagram. Ellingham diagram, when you will see in that diagram, actually it will this for both aluminum and magnesium. For aluminum oxide also one curve is there, and for magnesium oxide also curve is there. Two curve is there, and both curves are cutting at a point. That is marked by some point like red, blue, green, something may be there. It is marked. Okay, both are intersecting at a point. Correct? Then now you have to suggest the condition under which magnesium can reduce alumina. Then now two reaction you have written. Both are oxide reaction. One is aluminum oxide, other is for magnesium oxide. Now after that you see the diagram, Ellingham diagram I will send. Okay, you can see there. Then at the point of intersection of aluminum oxide and magnesium oxide curve, marked by some mark will be there, maybe from the you can say any point like H. Suppose H point is marked there. Then here what you will see, their point In diagram, the delta G, standard delta G becomes 0 for the reaction. At that point, now you will see, at that point, they may be marked by the red also. Then at that point, delta G value, standard delta G value, you will see the delta G becomes 0 for the reaction. For which reaction it will be 0? Then which reaction? Then this now combined reaction you are writing 2Y3 Al2O3 plus 2Mg, it is giving 2MgO plus 4Y3 aluminum. Means from aluminum oxide you are getting aluminum. Okay. Then for this reaction, balanced reaction is, that reaction actually you have combined. What we have written above two reaction, it is in a combined way. 2Y3 aluminum oxide plus 2Mg plus 2Mg. Okay. Direct reaction between aluminum and magnesium. Now you are writing direct reaction between aluminum and magnesium. Aluminum oxide plus magnesium means 2Y3 Al2O3 plus 2Mg. You will get 2MgO plus 4Y3 aluminum. Now you are getting aluminum reduced. Aluminum metal you are getting. Then at this reaction, for this reaction here, delta G becomes 0. Delta G becomes 0 for this reaction. Then below this point, below that point, magnesium can reduce alumina. Okay. Here you see important things, that first reaction you have written aluminum was giving aluminum oxide. Second reaction was magnesium was giving magnesium oxide. Then here you see now both reaction you are combining. Both reaction, oxidation, reduction. Then here aluminum oxide, when it will react with magnesium, only then it will convert to the aluminum. Aluminum oxide, first reaction, you got aluminum oxide. Now aluminum, from aluminum oxide you want aluminum. For that it has to react with magnesium. Magnesium, that is actually reducing agent. Magnesium is reducing agent here. Then after the reaction you will get aluminum. You are getting 4Y3L in balanced equation. Then when this reaction will take place, that time actually delta G value will be 0. Okay, this is an important thing. The delta G, standard delta G becomes 0 for this reaction, means 2Y3 Al2O3 plus 2Mg, it becomes 2MgO plus 4Y3L. Okay. Then for this reaction, delta G becomes 0. Then in graph you can see diagram, that point. Then below that point A, suppose it is A, then below that point it will be delta G will be negative. Delta G will be negative. Okay. Below that point magnesium can reduce alumina. Means after getting the intersection point, that below that point, what is the value for delta G? Any value below that point, just to see from y-axis, and means suppose it was A intersection is A point. Then from A, what is the value of delta G? You can see. Then below that, any value below that, this will be this reaction can takes place. Correct. Below that point magnesium can reduce alumina. Okay, then temperature also you are knowing on x-axis you can see, and delta G, what value of delta G, whatever be the value of delta G, just at point of intersection means A, below that magnesium can reduce the aluminum oxide. Okay. Now second I am telling you, second problem, although I am reading, although thermodynamically feasible in practice, magnesium metal is not used for reduction of alumina in the metallurgy of aluminum. Why? This question is asked. Again you understand, just I am telling the question. Although thermodynamically feasible, just now I told you, although thermodynamically feasible, in practice magnesium metal is not used for the reduction of alumina in the metallurgy of aluminum. Why? Question is asked. Then I am giving the explanation. Temperature below the point of intersection, temperature below the point of intersection of aluminum oxide and magnesium oxide curves, magnesium can reduce alumina. That is clear, that magnesium can reduce alumina, but the process will be very, very costlier. Okay, uneconomical, not economical, uneconomical. Okay, that's why in practice magnesium is not used. Okay, now one more question is there. I am reading, then I will explain. Why is reduction of metal oxide easier if metal formed is in liquid state at the temperature of reduction? Again I am reading the question. Why is the reduction of a metal oxide easier if the metal formed is in liquid state at the temperature of reduction? Means in liquid state it will be easier. Why? This is the question. Okay, why is the reduction of metal oxide easier? This is the question. Why in liquid state? And now I am telling, just I will give explanation. The entropy is higher if the metal is in liquid state. Correct? The entropy is higher, means you know that when it is in solid, entropy will be substance will be stable. Substance will be stable. Stable means this entropy is less. Entropy is less. Entropy less means stability. And when it is in a liquid or gaseous state, then now it is disturbed. Original arrangement is disturbed. Then now disorder, it went into disorder. That's why entropy will be more in a liquid or in gaseous state. Then this is the main point. The entropy is higher if the metal is in liquid state than when it is in solid state. First important point. The value of entropy change means delta S of the reduction process is more on positive side. Okay, the entropy change of the reduction process is more on the positive side when the metal formed is in liquid state. Obviously same things in different way, that when it is in metal oxide form, that time also it is a positive side, that is called positive side, more entropy. Okay, when it is in liquid state, and the metal oxide being reduced is in solid state, because from solid state it is less, entropy is less, in liquid state entropy is more, that's why it is easier. Thus the value of standard delta G becomes more on negative side. Okay, negative sign, delta G value I am talking about, when delta S will be positive, correct, means more and more, entropy is more and more, then delta G becomes, you can say, more on negative side of the reduction, and it becomes easier. Okay, delta G value is becoming negative if it is in a liquid state, means if entropy is more. This is the only answer. That is, if it is in a liquid state, entropy is more. Okay, more on positive side when the metal form is in liquid state, and the metal oxide being reduced in solid state, from means reactant is metal oxide solid state and product is metal in liquid state. Then now delta S is more and delta G will be negative. Okay, thus the value of delta G becomes more on a negative side. That's why it is easy. Easy means reduction is easy. Reduction becomes easier. This I have told about the, you can some this problem. And now actually application is there. Application of this Ellingham diagram I will discuss in the next class. Okay, thank you.